So there exists a randomized algorithm with high probability that outputs a cut S and S bar of G. So here is G, and here is our sparse graph, which is embedded into G. And so we have S and S bar, we have a cut, and an expander H on V. Both of them use the same vertices. Both H and G use the same vertices, and an expander H that can be embedded in G with congestion at most order of log 2n over phi of S. Note that this constitutes a certificate proving that phi of S is less than order of log 2n phi of G. So the expansion of any S is less than this factor times expansion of G. And the cut matching game creates the aim of cut matching game is to produce such an edge that we want, that has good properties. And so by going from find bisection, which is the cut player does the find bisection algorithm, and the match player does flow match. So these two players, when they go and after some time of the order of log 2n, this amount of Max-Flow computations you need in order to find such an edge that has good properties. I mean, so that edge could be embedded into G. So the cut player likes to minimize T, the rounds. The cut player he wishes to minimize T, and the match player wants to delay it, so maximizing T, such that for both of them we want HT be expander, and both of them have the constraint that HT we want to be expander. So it takes some time. For example, the first cut is like this, the other cut. After several cuts, I mean, T is equal to 1, T is equal to 2, and here T is equal to order of log 2n, as I said here. So it takes this amount of time such that so that H becomes a good expander and has a and so we want to round L. So we have the rounding of L. So we have find bisection. It gives a partition of BL and BL bar. And you give it to Max-Flow, it does the matching and then give you the matching you want. So LP linear programming for maximum bipartite matching. This can be formulated as LP. I mean, it's the same LP for Max-Flow, because in maximum bipartite matching, which is the action of the matching player, you want to say that you want to maximize Xij, such that Xij, for example, is 1 if it is matched. If I and j are matched, Xij is 1. If xij is 0, it means they are not matched. So in order to solve this efficiently for the match player wants an algorithm, and we give them this linear programming to match player so that the match player could run this algorithm and realize that he realizes that this is the answer to the matching problem. And also xij is less than 1 for any j in V. And ing is in E. Here again, ing is an edge. So, for example, first of all, we relax it to instead of just 0 and 1, which is just discrete, we let it to be a continuous. So it's between 0 and 1. So we relax it this way. And it is interesting that it turns out that LP for max flow is the same thing. So the maximum of X and S and J, or let's say maximum of I and T, S and J, S is source. If this is an edge, for example, overall, for example, I minus 1, I minus 2, all of them goes to J. And from this, you go out. So if this is the, for example, you want to take care of source, it means that all of the flow that's coming out of source, for example, S and J is, for example, is 2, J is 1, J is 3. All of them that are going out is, all of them, for example, go to some T, some sink, some target. And so instead of this, you can formulate it as xint. But the point is, all of them, xij, should be less than the capacity. And this is the capacity. So for any vertex I, the incoming flow must equal outgoing flow. So this is another constraint, xki, and xij is greater than 0. But remember that the match player wants to solve this problem. And if you just let xij to be, cij, the capacity, to be 1, so if you just, because xij is less than capacity, so if cij is 1, is the capacity is 1, then this one is reduced to max flow problem. So maximum bipartite matching is like max flow problem. So you see, they are equivalent. So solving this is like solving this if and only if your capacity is just 1. So we reduce maximum bipartite matching to a max flow problem, as you see. And so what we are going to do is that we add a vertex S to every vertex in your graph, to all of the vertices. So add a vertex S to all of the vertices, and the capacity is just 1. Capacity is always 1 for every vertex. And then add a vertex, and then we add a vertex, for example, to target. So we add a vertex T for any edge. For example, this is V and this is the target. And again, the capacity is 1. The capacity. And then we make every edge directed, like this, directed. with capacity 1. And this creates an instance of max flow. So instead of solving an instance of maximum bipartite matching, we are solving an instance of max flow. And so finding the smallest capacity, C of L, I always imagine like this, that you have a max flow solver, and in this algorithm you give a capacity CL. You say, this is my capacity. Let's see with this capacity what happens to the flow. And you solve this, you get some flow. And because in this algorithm you want to fix the flow to be n/2. And then you have a controller, feedback controller. This is a controller that says how much you should change CL. Should we move it up? Should we decrease it or increase it? And we increase and decrease CLs as long as we have a flow of n/2. For example, if sometimes you give a CL that the flow is greater than n/2, so we reduce CL. We reduce until flow becomes n/2. So this is like a control problem. And the analogy with a control system allows you to understand what we are going to do. So we fix this flow and see what happens to capacity. And it's just a binary search. So a bisection search, or let's say binary search. And we find the smallest, this capacity CL, smallest CL on G. That gives a flow of n/2. And the flow can be decomposed into flow path, yielding a perfect matching across the bisection. For again, my example, for anything that goes here, for example, we want to go from I to J, one commodity, and in H, this represents an edge, IJ. Going from IJ, H is weighted, but G is not weighted. And so there are different ways that we can go to J. There are different ways that we can go to J. But I and J, the demand is sitting here. And H is the sparse graph that is embedded into G. So as I said, we keep flow constant, n/2. So sum of the flow that goes here, F1, F2, F3. So if you sum over all of the flow that's going out of your source I, is just, you fix it to be n/2. And then you notice, for this problem, you get a C. C is something, for example, some number. You get some C. And that's the C that we are interested in. And I mean, so the flow can be decomposed into flow paths, as you see. There are 3 passes. And yielding a perfect matching across the bisection. So this is a cut. This is a cut. So this is S. So for example, for any S and S bar, you can see that there is an equivalent here. And this is the intuition behind that. The cut of H is even less than the cut of G. And you will see that in several papers. And the flow problem, so the matching can be routed through G with congestion at most C of L. So the capacity that I set to that black box solver, which is a max flow solver, to get flow of n over 2, and here you give capacity, C of L. So if the edge capacities of G's are reduced to CL over 2, the flow problem is no longer feasible. And then the mean cut yields the partitioning of S and S bar with edge expansion at most 2 over C of L. Of course, we will show it. And so let us estimate how well the worst of O log 2n cuts that SL and SL bar. So that approximates the sparsest cut in G. And we use the property that the union of edge of the order of log 2n matching can be embedded in G with congestion, with some congestion. So what we are doing is that I should show you with some pictures. You have a graph with some vertices 1, 2, 5, 3, 6. And so you have a cut here, a cut, for example, this is a cut at round 1 of the cut matching game. This is just a cut. So a cut 1 and 4 are cut. 2 and 5 are cut by this cut. And 3 and 6 are cut. They are cut. And the matching player uses these, they match these edges, they find a match. And then at round 2, you have another cut goes here, for example. This is another at round 2. So this game has several rounds. At round 2, we have another cut. And for this cut, 4, the match player is now is matching 4 to 6. The match player is now matching 1 to 5. The match player is now that's it. You have found all matchings that is possible in this. And of course 3 could be connected to 2 because we are at round 2. And so you have S and S bar, let's say A1 and B1. So 1, 2, 3 goes to 4, 5, 6 at round 1. So this is connected to this. This is A1 and this is B1. And so this is the round 1. As you saw in round 2, 1 is connected to 5, 2 is connected to 3, 4 is connected to 6. And this is B1 and this is A1, this is round 2. And this goes on until round order of log 2n, that you have your graph H. So H is being constructed. So this is H. That sparse graph that we were interested in that. But this H is just a summarization of or compressed form of the G. I mean, the vertices of G and H are exactly the same, but their edges are different. G is not weighted, but H is weighted. And so you see that H is embedded into G. And this is interesting. And you can compare, you can see that their cuts is almost the same. And the cut of H is less than the cut of G. And you will see that in several papers.